Hello everyone, thank you for attending the presentation today. My name is Basem ElHalawany. I am with Electronic and Communication Department at KCST. I'm presenting today our paper, Next Generation IoT Connectivity, FSO-RF integration with a high altitude platform for reliable data transmission. I would like to thank my collaborator from Space Technology Center at Egypt, and Banha University at Egypt, University of Victoria, and Southwest University at China. Our outline is a background and motivation about the work, proposed high altitude platform-based network, and numerical result and conclusion and future work. Through this day, we have seen a lot of presentation talking about the large number or the huge number of IoT devices connected to the network, and how to deal with this amount of data in terms of AI and security. But no one speak about how to provide this global coverage and how the network will respond and how to achieve this connectivity. So today I will take you in a brief dive in how we provide a solution for such network. Next generation wireless network need to provide a solution to deal with a huge amount of data. So there are many solutions and prototypes that try to deal with the problem. Today I will speak about one of the proposed group of network. It's called non-terrestrial networks that depend on devices that are flying in the Earth space or in free space outside the Earth. This technology include LEO satellite constellation network, where there are 100 or 1,000 of satellites that rotate in many orbit around the Earth. With a huge number of satellites, we have many difficulty in communication and moving the connection from one satellite to another. Another example of such NTN network or non-terrestrial network is low-altitude platforms such as drones, but this has a lot of limitation in terms of the lifetime of the battery of the drones, so it can help as a temporary solution for the global coverage in certain small area, of course. The third option is the high-altitude platform, HAPs. This solution constitutes of a lot of platforms that can fly in the Earth's atmosphere for a certain amount of time. There are many prototypes now that can fly over multiple months. Today we will try to propose a solution for global coverage based on high altitude platform. These are examples of the current prototype in different countries related to HAPs. The first one is the Sun Glider at Japan, is a property of SoftBank. It consists of a huge wing that carry solar cells that can keep the drone rotating in around certain area for around 1 month. Also, there are tries at United States. NASA has provided Helios. It is some similar design. It depends on the same concept, rotating around a circular area for some period of time, maybe months or two. Also, there are tries to use balloons. Balloons can provide more efficient flying time. It can stay for longer time because it can hover at the same position. This will be more advantage in terms of stability of the communication with IoT device on the ground. So today, we are trying to propose a system for using such a HAP platform. Okay. All of these HAP platform till now depend on radio frequency in the license band. We make communication with the ground station or with the IoT device on the ground using radio frequency signals, which is a license band, and we must pay for this communication if you want to communicate with the IoT device. So the cost for transmitting 1 bit in such non-terrestrial network, including satellite, including low altitude platform or high altitude platform, is still high. We need to achieve a global coverage in addition to low cost for communication. So radio frequency or RF signal is not enough to solve this problem. So we need another solution with HAPs. The proposed solution is using another type of signals, which is a free space optical signal. It is some sort of a laser communication, but it has some limitation. It can give us a lot of capacity. We can send a lot of data from transmitter to receiver using optical signals in the free space. This is different from optical fiber communication. Optical fiber communication, we need to extend optical fiber cable between the transmitter and receiver. But here in free space optical, we can send the laser signal directly in the free space. So we have a lot of bandwidth. It is not chargeable. We don't pay money for sending data through RF because it is not licensed spectrum. But there is a limitation, of course. Everything has its pros and cons. The disadvantage of using free space optical communication is that we need to have some sort of accurate alignment between transmitter and receiver. The existence of misalignments lead to degradation of the communication between transmitter and receiver. Also, it can be affected by turbulence in the free space. It can be affected by dust particle. It can be affected by fog. So we need to solve the problem of global coverage. We need to have low-cost transmission, and at the same time, we need to have a stable communication that provides a global coverage. So our proposal is to propose a hybrid system that use or benefit from both radio frequency and free space optical communication with the HAP technology for provide a stable coverage on the Earth. So our proposed research is providing or developing a HAP-based network solution that can satisfy the demand of global coverage via using the radio frequency signal because it has a large coverage area. Also, we need to boost the throughput in certain high demand area with a high number of IoT device, or it need a high gigabit per second to be transmitted. So for this, we will use the free space optical signals. Our methodology will develop a closed form analytical expression to characterize the performance of the proposed system in terms of closed form equations. We can substitute any parameter and define its effect on the system. This is a big gap in a communication system. We need to find closed form equation, not just simulation, not just using simulation. Our proposed HAP-based network solution, we investigate the performance of a single HAP platform as shown in this figure. This HAP platform is equipped with two types of communication interfaces. One is a free space optical interface, and the other is a radio frequency interface. With both interfaces, we can communicate with a large number of IoT devices. As an example here, we have some concentrated region with high number of IoT devices, maybe in a factory, on a stadium with high number of people, in places where we have a large number of users need to be connected. So in this case, we assume we have some sort of collective access points. This access point can communicate with its surrounding IoT device, while we may have also some IoT device that at remote position or rural positions that we have a low number of IoT devices in such area. So we have multiple access points with certain diameter, can communicate with its nearest IoT device through the free space optical communication links. And the HAP can communicate with the remote IoT devices through the radio frequency signals to provide a global coverage for the area. In urban hotspot where a large number of IoT devices, the HAP can communicate through the free space optical communication link with the HAP, while the IoT device can communicate through the radio frequency to the access points. While in the remote region, it depends only, IoT devices only depend on radio frequency communication. So in this case, through this design, we can achieve both global connectivity and global coverage, and at the same time, we can give the IoT device the ability to transmit a large number of data through the access point through the free space optical link. In our network operation, we give priority to data transmission to the access point through the free space optical link, since it serves a large number of devices around it. When the access point achieve a good communication with the access point, there is a good communication between the hub and the access point, we use the free space optical link. But also we assume that the access point can communicate with the hub through radio frequency signal, because as we said in the beginning, the free space optical link can be interrupted due fog, due turbulence, so we need to have another backup for the access point. We use a hard switching mechanism. It's a very simple hard switching mechanism. If the quality of the communication between the hub and the access point is below certain threshold, through the free space optical link, the access point directly transfers its communication to use radio frequency signals. We give equal priority to the number of deploying access point, so the hub can distribute its communication power to the large number of access point in the vicinity or in the coverage of the hub. We derive unified analytical expression for one of the most important metrics for the communication network, which is the ergodic capacity. The ergodic capacity is the achievable capacity of the network, but average over all the possible fading channel distributions that can exist. So we have here two types of channels, the free space optical channels, and we assume it follow a gamma-gamma fading distribution, and the Raytian fading channel for the RF signal. So taking those into consideration, we derive closed form expression for the achievable ergodic capacity of the system. We also use Monte Carlo simulation to make sure that our analytical expression is accurate. In the following, we show the result of our derivation and simulations. In the first figure here, we compare the achievable capacity for each access point. We deploy, in this scenario, we deployed 5 access points under the coverage of the hub, and a large number of IoT devices is deployed near the access point and in the remote areas. In this figure, we can compare three curves. The first one is the red one, which show us the achievable ergodic capacity for each access point as a function of the transmit power of the high altitude platform. We see here the red curve that increasing as we increase the power, the achievable capacity of each access point is increased. For example, if we take a certain point as 25 dB transmission power, we can see that each access point is capable of achieving 14.5 gigabit per second, while the IoT device scattered in areas far from the access point can achieve a collective capacity of 2.5 gigabits per second. So the network can achieve in total 75 gigabit per second for this scenario. We also compare the RF only scenario where we only use RF signal. There is no free space optical signal. We can see that the whole number of IoT devices can achieve 8 gigabit per second. There's a very large difference between the combination of radio frequency and free space optical systems. To test the scalability of our system, if we increase the number of access points deployed under the coverage of the hub system, we assume that we increase the number of hubs from 1 to 10, and we can see that the proposed system can achieve, if we deploy 1 access point with the hub power, we can achieve more than 25 gigabit per second for 1 access point. While if we increase the number of access points, the hub power is divided equally between the multiple access point. We can reach around 6 to 7 gigabit per second if we have 10 access points. So in this case, we have to make a trade-off between number of access points and the achievable capacity per access point. At the same time, we can see that the remote IoT devices also is affected. If we increase the number of access points, we see here that using only RF, the green curve, we have around 6 gigabit per second if we have 1 access point. If we increase the access point, we have around 0.2 gigabit per second for the whole number of IoT devices. This because of entanglement between the radio frequency and the free space optical communication in the proposed system. What about the limitation of such a system? We, from the beginning, said that free space optical have some limitation, and this limitation usually is expressed in terms of the misalignment error. If we have, we can characterize misalignment between the transmitter, the HAP, and the receivers at the access point using certain parameter or coefficient. It's called the misalignment coefficient, epsilon. When epsilon equal to, for example, 5, this means that we have near perfect alignment between transmitter and receiver. In this case, we have a good capacity achieved for the system. If this number, the epsilon, is become 2 or 1, we have misalignment error. The free space optical communication can't be achieved perfectly, and the ergodic capacity achieved for the system is reduced, as we see here for epsilon equal 2 and epsilon equal to 1. In conclusion, we proposed a HAP-based network with parallel free space optical radio frequency transmission that maintain a global coverage through the radio frequency communication and very high speed communication through the free space optical link. The proposed solution can enhance the overall efficiency of the IoT communication system. This system can be enhanced by certain future work, including adding error control mechanism, dynamic resource allocation, or even using machine learning to control the sky network. Thank you.
Thank you very much, Doctor, for the well-done presentation. Very interesting topic on next generation networks. And we are running a little bit behind on schedule. If we have one quick question or one quick comment, we can take one. Yes.
Thank you very much, Dr. Basem. Actually, the good thing about such work, I mean, the application to disaster response, but my point is you verify simulation and analysis, which is great, because now most of the work, they only do simulation, so that's great work. My comment, when you mention about multiple access points, there is a degradation in the ergodic capacity, like so what is the architecture of these access points? Like, are these like point to point until, so when you increase the number of access points,
okay.
What is your architecture?
This is a proposed design. We have multiple access points. Each access point is equipped with the two interface, radio frequency and the free space optical interface. The HAP is communicating with each one of the access point either through free space optical if the link is good, and in situation where the channel is free space optical channel is weak due to turbulence or fog or dust, automatically the HAP and the access point switch communication to the radio frequency. So we have two interface in HAP and two interface in the access point.
Very good. But when you increase the number of access points, normally you don't select the best.
No, we communicate with all access points.
Okay,
because of this, the achievable ergodic capacity is decreasing.
Makes sense. Thank you so much. Appreciate it.
Thank you so much again, Doctor. Now we'll be moving on to the next presentation.